Our first speaker will be Lorenzo Ruggeri, who will tell us about non-invertible duality defects in 2 + 1 dimensional QFTs from half space-time gauging.
Thanks. So, as you see from the title, I'm going to talk about non-invertible duality defects in today's talk. This is based on some work that appeared last June with Wei Cui and Babakar Gat from the Yao Center at Tsinghua University. Okay, so first, to introduce this topic, let me briefly summarize the concept of non-invertible symmetries that has drawn a lot of attention in the past few years. So the idea is that in a relativistic quantum field theory, that we know that to each ordinary invertible global symmetry, there is a topological defect associated to it. Now, what we can understand is whether the opposite is also true. But we know that this cannot be the case, just as simple statement as this, because we know that already in 1 + 1 dimensional quantum field, 1 + 1 dimensional quantum field theories, there exist some topological line defects which satisfies fusion rules as follows, where on the right-hand side we do not only have a single object, but we actually have a sum over multiple objects coming with some positive integer coefficients. Something like this already happens for the Ising model in 2D, so a very simple model. So we already know that if we want the converse to be true, we also need to allow for non-invertible symmetries. So these are symmetries that I think most of you already know these. They are symmetries that do not follow a group-like composition, and such that they do not admit an inverse L-1, such that L times L-1 is equal to the identity operator. So in the literature, there are many constructions of non-invertible symmetries, and among all of these, I will focus on just duality defects. These have been introduced in two papers from 2021, one by Choi, Cordova, Sin, Lau, and Shao, and one by Kaidi, Omori, and Zheng. And the idea is that if you take a QFT Q, and this QFT has a non-anomalous P-form symmetry G, we can always gauge it and consider a new theory Q quotient by G. And whenever this new theory is equivalent to the original one, this defines a duality defect. So now there are two main constructions, or let's say even two constructions, to find such defects. The one is via half space-time gauging, and the simplest example is that of 4-dimensional Maxwell theory at a particular value of the coupling constant, and this will be a recurring theme in all these examples, that only at some values of the coupling constant this happens. So these theories have an electric symmetry, which is a U1 one-form symmetry. The symmetry operator generating this symmetry is eta, just e to the star f integrated over 2 cycles of the manifold, and this acts on Wilson line, shifting the gauge connection. Now what we can do is that we can gauge a Zn subgroup of this symmetry, and this has the effect of rescaling the gauge field to A over An, and since Maxwell theory, the action is quadratic in A, the effect is just that of sending tau in tau over n squared. On top of this, we know that Maxwell theory also has a S-duality, which is an isomorphism between two different theories, one at tau and one at minus 1 over tau. Notice that this is not a symmetry at generic values of tau, it's a different concept. Only at value of tau equal to I, it's actually a symmetry. So now we can put these two defects one next to each other, the one implementing this codimensional one defects implementing sigma implements gauging, and S implements S-duality. And then we can collapse the two defects together and get a new defect, N. And the effect is that on the left-hand side, you start with Maxwell theory at gauge coupling tau, and the right-hand side, you have Maxwell theory at gauge coupling minus n squared over tau. Now, at generic values of tau, these are two different theories. Only at a specific value, exactly this one, the two theories become the same one, and this N defect is actually a symmetry, it's actually a symmetry. And turns out to be a non-invertible symmetry. The worst volume of this defect can be shown to be some BF theory, with the two gauge connection on the left-hand side and the right-hand side of the defect appearing. And the non-invertible nature can be seen by computing the fusion rule of n with its orientation reversal, bar n. And the idea is that if you compute this fusion rule, you get on the right-hand side a condensation defect, which is basically means that you are one gauging or gauging on a codimension one submanifold this Zn one-form symmetry. This concept has been introduced by Rumpedakis, Seif Nasher, and Shao in 2022, And so the idea is really that you have to sum over all two cycles of the manifold, the operator eta, the symmetry operator for the one-form symmetry, evaluated on that two cycles. For the rest of the talk, I will call C this symmetry operator, this condensation defect that will appear many times in this talk. The other construction that appeared in the other paper I mentioned before is that of starting from a theory with, let's say in 4 dimensions, you start from a theory Q prime with a Z2 zero-form symmetry and a Z2 one-form symmetry, and these crucially need to have a mixed Tooth anomaly. And the mixed Tooth anomaly is the following form, where A1 and B2 are the two background fields for the two symmetries, and P is the Pontryagin square. And the idea is that if you gauge the Z2 one-form symmetry, you find a new theory which I label Q. Everything is fine, but the defect D that generated the Z2 zero-form symmetry now is not gauge invariant anymore because of the mixed Tooth anomaly. So it, in principle, does not represent a well-defined symmetry. However, we can couple it to a TQFT such that the combined anomaly of the codimension 1 object vanishes. And as it turns out, this TQFT, three-dimensional TQFT, is U1 level 2 Chern-Simons theory, which is a non-invertible TQFT, and this gives rise to the non-invertible nature also in this case of the duality defect. Also in this case, the duality, the fusion rule with its orientation reversal gives this condensation defect. Now, example of this Tooth anomaly construction of duality defect, there are many in the literature. One is time reversal in 4D Young Mills at a specific value of the theta equal to pi. So it combines with the one-form symmetry, electric one-form symmetry, and also the axial symmetry in 4-dimensional QED and 4-dimensional quantum QCD. The idea is that all defects that admit a Tooth anomaly construction also admit a half space-time construction, while the vice versa is not true. So there are some that can be constructed by half space-time gauging that cannot be constructed in the opposite way. So now, to study this non-invertible symmetry is a concept that is very useful, and it has been very useful also studying generalized symmetries more in general, is that of the symmetry TFT. It has been applied to study non-invertible duality defects in a paper by Kaiju, Mori, and Zheng in 2022. And the idea is that you take a topological field theory on a slab in D+1 dimensions, and the idea of this symmetry TFT is that it decouples the dynamics of the theory Q that you want to study in D dimension from its symmetries, let's say P-form symmetry G. And crucially, for the rest of the talk, it's independent on topological manipulations of the theory Q, as I will motivate momentarily. The idea is that on the two sides of the slab, so this is the slab, where the TFT lives in the bulk, on the two sides, you can, on the left-hand side, you put some topological boundary condition, either Dirichlet or Neumann. So where the Dirichlet boundary condition sets to a specific, sets all, the set of all flat connections for the symmetry GP to a specific value capital A, and similarly the Neumann boundary condition do something similar for the dual fields, for the magnetic fields, if you want. On the right boundary, instead, we have a physical boundary. Here you have to sum over all flat connections of your symmetry G, each weighted by the partition function of the theory Q at the value A. And the idea is that, let's start from the Dirichlet boundary condition on the left. When you shrink the slab, you only get the D-dimensional theory Q. And this can be just seen by taking this, sandwiching this, and this. It's vice versa. As I said before, the Neumann boundary conditions are basically Dirichlet boundary condition for the dual fields. And so in this case, when you shrink the slab, you don't get the theory Q, but you get the theory Q quotiented by this P-form symmetry G. And then you see that topological manipulation that, for example, send Q into Q quotiented by G so these two theories share the same symmetry TFT. So you see that this symmetry TFT is already useful for describing non-invertible duality defects. So an interesting, so these non-invertible duality defects can fall into different categories, group theoretical and intrinsically non-invertible. The idea is that a non-invertible duality defect eta in Q is said group theoretical if it can be mapped via topological manipulation as gauging or stacking with an SPT phase to an invertible defect in Q prime. Sometimes it is called also non-intrinsic non-invertible. Otherwise, it's denoted intrinsic duality defect. So we already see that all duality defects constructed via 't Hooft anomaly, they need to be by construction group theoretical. The reason for this is that we really started from a theory Q prime with only invertible symmetries, and then we gauged, so we did some topological manipulation, and we found a new theory with actually non-invertible symmetry. So all those constructed in that way are by construction group theoretical. So if you want to look for some intrinsic non-invertible duality defects, these need to be obtained via alpha space-time gauging. Now, as I told you, as I tried to motivate before, these symmetry QFTs are invariant under topological manipulations, and so they can be used to determine whether the duality defect is intrinsic or not. And this has been studied in a paper by San Zheng from last year, and the result is the following, is that the symmetry QFT of a theory with non-invertible symmetry is when the symmetry QFT of the theory with non-intrinsic invertible, non-invertibles. Let me start again. So the symmetry QFT of the theory with invertible symmetry is a gauged anomaly theory, and this is just a digraph within theory, and the same is true also vice versa, which means that if we start from a theory which has a non-intrinsic or a group theoretical duality defect, the symmetry QFT will be a digraph within theory. So for example, this has been studied in 4D, gauging in half of space-time as Z1 and symmetry, and the idea is that they found that the symmetry QFT is a digraph within theory for only specific values of n, and similar results also are true for two-dimensional. So the idea is that the space of group theoretical defects is just a subset of the. There are many duality defects that are intrinsic non-invertible and that cannot be described via 't Hooft anomaly construction. So what we tried to do in our work was to extend this construction in 2 and 4D that are already known in the literature to three-dimensional defects. Here the story is a bit different. Some duality defects that are non-intrinsic or group theoretical are known. They've been studied in this paper, and the idea is that you start from a theory Q prime with a mixed anomaly between these three symmetries, and then you gauge 2 of them, and then the remaining zero-form symmetry actually gives rise to an invertible symmetry in the same way as before by stacking with some non-invertible topological field theory. But there was no construction of duality defects in 3 dimensions via half space-time gauging. That's what we did in our paper. So now we start with the theory Q with these 2 symmetries, and clearly they need to have a vanishing 't Hooft anomaly because what you want to do is to gauge both of them and define a new theory Q. And we wanted to understand what happens when these 2 theories are the same. And later on, we will provide I will provide some examples as well of certain theories that share this property. So the idea is that the fusion rules, in the same way as before in 4D, now they generalize those ones, because now on the right-hand side, if you take the duality defect in 3 dimensions and its orientation reversal, you find that you're not only condensing the one-form symmetry Zn, as in the previous example, now you're also condensing the Zn zero-form symmetry, the 2 of them that you are gauging on a codimension one submanifold. So also in this case, you're doing one gauging of these 2 symmetry on a codimension one manifold. Now, what we studied as well was this 4-dimensional symmetry QFT of these theories, first starting without not assuming these invariants, and later on I will demand this to be true. So the idea is that the symmetry QFT of theories with a Zn zero-form symmetry and Zn one-form symmetry is just a 4-dimensional BF theory where now A1 and A2 are the electric and magnetic, let's say, one cocycle for the Zn zero-form symmetry, and B1 and B2 are the electric and magnetic 2 cocycle for the Zn one-form symmetry. And together, the symmetry operator, so we have for each of them, so these are the symmetries in 3 dimensions, then we extend them in 4 dimensions, and so the Z1 symmetry becomes Z2 and the Z0 becomes Z1, and we have both the electric and the magnetic. This is standard in symmetry QFT, and so these are the full symmetries of the symmetry QFT, and they are generated by some lines and surface operator in the bulk. Crucially, on top of these 2 symmetries, there is also an electromagnetic exchange symmetry that exchanges the electric and magnetic component of those generating the 2-form symmetry and of those generating the 1-form symmetry. And now it's one can understand that the defect that generates such Z4 electromagnetic symmetry is that of one gauging the Z2n and Z1n symmetry on a codimension 1 manifold. You can see this by taking codimension 1 defect, implementing this truth transformation, and you take some lines L and S passing through the defect from the left to the right. If you take those to the right and you fold them back to the left, these two combined are absorbed in the defect because you don't have anything else on the right left, and these ones that are absorbed exactly because of this action are those that you expect to be absorbed by a defect that implements one gauging of these two symmetries. So now we have that the generator of this Z4 electromagnetic symmetry is this condensation defect. And now we want to take this condensation defect not on a codimension 1 manifold, but on a codimension 1 manifold with a boundary. So on M3 with a boundary M2. And this defines these twist defects V0 that are crucial in understanding the gauging in alpha of space-time construction that I'm about to show. So now we can try to understand what happens when we impose that the theory is actually equivalent to the theory after gauging. And the idea is that the bulk of this twist defect becomes transparent because when you gauge this group, you only restrict to lines and surfaces that are gauge invariant, and so those that remain don't see this condensation defect, and so this twist defect, the bulk of it becomes trivial, but crucially, the boundary, that leaving M2, it's still non-trivial. So we see what happens before and after imposing this condition here. So on the left-hand side, we have not imposed this condition, and you have the twist defect, which is codimension 1 with a boundary. Then you shrink the slab, and you find that on the upper part, you have the theory Q. On the lower part, you have the theory Q quotiented by these two groups, exactly what this was doing the twist defect V in the bulk. And this defines an interface between two different theories. Now we said if we impose that these two theories are the same, the bulk of the twist defect becomes transparent, and when you shrink the slab, you only have codimension 1. You only have the boundary of the twist defect acts on the after shrinking, and then you have that this twist defect is exactly the one that implements half space-time gauging, and it's the non-invertible symmetry defect that we were looking after. Now, one can also study the symmetry TFT of this. One can study also the symmetry TFT for the Z4 gauged version, and this is just a BF theory where now you have to gauge this. I can present. It can be given an explicit expression, and now one to connect with terminology we used in many other cases. For example, for the Ising model, the full symmetry is the higher categorical analog of the Tambara-Yamagami category for now the product of the two symmetries. Okay, so now I can finally present some examples of theories admitting such duality defects. The first one is just the U1 times U1 gauge theory, and here you have, so basically Maxwell theory, but now two U1 factors. So the idea is that now you have two copies of the electric one-form symmetry and two copies of the magnetic zero-form symmetry because we are in 3 dimensions. What we can do is that we can gauge a subgroup of the magnetic zero-form symmetry and a subgroup of the first factor and a subgroup of the electric one-form symmetry of the second factor. So we gauge a subgroup of this. On top of this gauging, we also have some θs transformation acting on the coupling constant E1 and E2 of the two gauge factors, and this take tau and descend it in. And if you take tau, so this ratio, you send it to 1 minus 1 over tau, you see that the symmetry is, the theory is equivalent. So now again, we want to combine these two things together, half space-time gauging of these two symmetries and this S transformation, and find that the combination of these two codimension 1 defects give us a non-invertible defect obtained by half space-time gauging. As before, the effect of gauging Zn0 and Zn1 is that just of shifting the coupling constant. Notice that gauging a subgroup of the magnetic one sends E1 into E1 times n, and as before, gauging a subgroup of the electric one sends E2 into E2 over n. So now we have that if we start with Maxwell theory at J-gauge coupling T, we act with gauging, we act with S-symmetry, we end up with Maxwell theory at, not Maxwell theory, sorry, U1 times U1 gauge theory. Crucially, this does not work on Maxwell theory. I can be more specific about that later. But anyway, you start with tau, U1 times U1 at value tau, you go back to, you arrive at minus n squared tau minus 1. These, for generic values of tau, this is different. And again, only at a specific value of tau equal to I over n, I times n, you end up with the same theory. And this defines for you a non-invertible symmetry defect in these theories. Again, the work volume of such defect can be shown to be the following. And we're now also this compact scalar, which is the electromagnetic dual of the gauge field for the first U1 factor, appears on the left and on the right. This is just a generalization of the duality defect I was showing before. Okay, so I only have 5 minutes, so I will skip this example, but this is just more generic product theories that have been also studied recently by these authors for lattice theories. And I will go directly to the last example. So I will start from a 6-dimensional equal to 2,0 SCFTs of type AN-1. So now the partition function of these theories is not a number, but is actually a vector in the Hilbert space of a set dimensional topological field theory. And this gives, and because of this, these 6-dimensional theories are called actually relative theories. And they live on the boundary of this 7-dimensional TFT. And now what we want to do is we want to compactify this 7D, 6D system to a 4D, 3D system, so that we can find on the 4D side the symmetry TFT, on the 3D side the theories that might have some non-invertible duality defects. So we start from the 7-dimensional action, which is the one of the 7D TFT. This is nothing as a topological subsector of some supergravity theory in 7D. And we compactify on 3 manifold. This is what we find, and what we find depends on the homology groups on compactification. So, because the original 7D action is this one, where C is a 3 form. And now whether C wraps some 2 cycles or 1 cycles in the compactification manifold, we will find a different action in 4D for our, let's say, symmetry TFT. It's a bit more subtle to actually get the symmetry TFT, but this is the idea. And where Qij is the intersection matrix of 1 cycle and 2 cycles in M3, and A1 is C integrated over 2 cycle, and B is C integrated over 1 cycle. Now, this is the 4-dimensional theory. On its boundary, there will live some relative field theory. And however, in this case, we can actually choose an absolute. We can go from the relative theory to some absolute theory in 3D by choosing a polarization for the compactification manifold. This is just a maximal isotropic sublattice of H1 plus H2 of the compactification manifold. And this choice of polarization will determine the symmetry of the absolute theories in 3D. Now, we can transform among all these different absolute theories. And one way to transform among them is to gauge some subgroup. Another way is to use the mapping class group of the compactification manifold, and this is just the group of diffeomorphism of M3 connected to the identity. And then, if we do this for a particular example, that of the connected sum of S2 times S1, this is what we follow. So in this, you find this is so the mapping class group in this case is the following, and we are interested in this Z2, that is the one that exchanges the two S1 times S2 factors as follows in the connected sum. This is part of the mapping class group. And on top of this, we also have gauging. So for example, for some choices of polarization, okay, I will be quick because I only have 2 minutes left. So the idea is that, as I said before, the absolute theories are given by a choice of polarization, and the choice of polarization is a maximal isotropic sublattice of these two groups, and these determine the symmetries. So if we take L1, so an element in here, an element in here, for one polarization, we find these two symmetries. So the electric, let's say, so lambda L1 is associated to electric, is an electric representative for the Z1 symmetry, and S2 is the magnetic, and vice versa. We do the opposite for lambda 4. So we have now the magnetic for L2 and the electric for the magnetic for Z1 and the electric for Z0. And now we see that if we combine these, that switches the two S2 times S1 components, so basically it switches the electric and the magnetic component for each of them. And we combine gauging, so let's say we can gauge this group here in lambda 4, or vice versa, we can gauge this one in lambda 3. This acts as follows, so going from lambda 3 to lambda 4 and back. So if we combine the two actions together on lambda 3, we go back to lambda 3. However, at the generic value at the value of the coupling constant, which is different than the original one. Since the value of the coupling constant is given by the ratio of these two volumes, we see that only at the value of the coupling constant equal to 1, so when the two volumes are the same, we actually have a non-invertible defect. So also in this case, we obtain a non-invertible defect via space-time gauging. that only occurs at some particular value of the coupling constant. So this is something very specific. It happened in Maxwell theory, it happened in U1 times U1 gauge theory, it happens also here. So, conclusion, this is the last slide. What we have found some non-invertible duality defects in 2 + 1 dimensional via space-time gauging. So they can be in principle non-intrinsic, and we also have studied the symmetry TFT, which describes these duality defects. We have presented some examples, such the U1 times U1 Maxwell theory, which is the simplest one we can present. I skipped the product theories. This is very generic, but can be done in a lot of cases, but there are some. I can say more about them. And then we also studied some of them via compactification. So some fusor directions, as I already mentioned during the talk, we can look under which of these duality defects are actually group theoretical, as this can be looking, one can just look at the symmetry TFT and try to understand whether there is a digraph Witten theory or not. Moreover, it will also be interesting to find some three-dimensional gauge theories, which are not product theories, that admit duality defects, and as usual, this can be obtained by gauging and using some duality, and given that there is a large web of duality in 3D, the two things can be put together. It is work in progress. And then, of course, one can consider also some RG, some deformation that trigger an RG flow for the theory to flow to the IR that preserves the non-invertible symmetry. This has been done recently, for example, for 4D n equal to 1 theories. And this allows you to study the IR phases of these dimensional theories and giving some constraint on the possible. Well, thanks a lot for your attention. And finish here.
Thank you, Lorenzo. Questions?
So this last. Sorry. So this last feature direction that you just mentioned, I think this is something that we are also trying to do, but not in 3D, in 2D. So when it comes to 3D, are there some specific theories such that you want to study their, deformation and their, RG flow to different IR phases?
Yeah, so it's a very good question, and that's something we are definitely trying to understand. So the idea is that for now, the theories that we know that have made these duality defects, unfortunately, are not extremely interesting per se. So we are definitely looking at, for example, one example that we are looking into is ABJ or ABJM theories in 3D.
Right.
And we're trying to understand if for some specific values of n or number of Chern-Simons level, there is some non-invertible symmetry, and it would be very interesting to understand if we find the deformation to the AR that preserves this non-invertible defect to study the vacuum in such theories.
Okay.
But I don't have a better answer than that. I'm sorry.
Okay.
We don't have any results on that.
No problem. Thank you.
More questions? Lorenzo?
So when we are studying RG flows in 2D, right, we have theorems like C theorem and other things like that. Do we have some additional theorems that come into play when we are studying RG flows in three-dimensional QFTs?
Yeah. So you're asking about theorem about RG flows in 3D.
In 3D,
well.
yeah.
Yeah, right. So I think in 3D there is some F theorem. I think it's called. I believe it's called, and the concept is very similar. That there is a quantity along the RG flow that constantly decreases, and basically gives you the amount of degrees of freedom. For example, the partition function of S3 can be used to I think there's a paper by Ferris, I think, doing that. So yeah, in principle.
Okay, if there are no more questions, let's thank Lorenzo again.
Thank you.